Lights in Three.js and React Fiber. They can be very powerful, but will also use a lot of resources, so let's learn how to use them properly. In Three.js you have 6 different kind of lights. Each one can be used for its own use case and performs better or worse than the other. Let's go over each of those lights so you know exactly how to use which one in your scene. But first we need to create our basic scene, which we are going to use to demo different lights. Start by changing the camera position and create a light scene function, which will contain all the code related to this video. Let it return a basic plane, which we will transform a bit to get it into the right size, rotation and position, and add it to the scene. To test the behavior of lights and the way it gets reflected from materials, we will add 4 torus knots that are rotating above this plane. Let's start with 1 torus knot and give it a position and set the material to a red mesh basic material. Now we can copy this 3 more times and change the materials to a standard material, Lambert material, and a matte cap material. The matte cap material will need a matte cap, so let's add one to our project. I downloaded mine from Nightorx's GitHub project called matcaps, which contains more than 600 matcaps, and added it to the public/matcaps folder. Retrieve the matcap in React using the use texture hook provided by React Tree Break. Create a reference and set the ref property for each torus knot. Use the use frame hook to run some code on every frame so that we can rotate all the torus knots by creating an array of the available references and loop over them. Update the rotation with a low value, and there you go. To start clean, let's also remove the existing lights on our base code. What's important to notice is that this only hides 2 out of the 4 toruses. This is because the mesh basic and mesh matcap material don't respond to lights, even though it might seem like the mesh matcap material does. During the video, you will see that no single light will have any effect on those 2 torus knots. Now let's implement the lights in order of best performance to least performance. That means we start with the ambient light, which is a light that will lit up every surface exactly as much as any other. Create an ambient light and set the intensity to a tweakable property which we create using Viva. I set the default value to the default value of Three.js, which is 1. The result will be a bit different to see for the mesh Lambert material, so let's set the color of that one to green. And as you might have seen already, using the ambient light on a material that responds to lights like the mesh standard material will give exactly the same result as using the mesh basic material without any lights. Now let's jump to the next light, which is the hemisphere light. This one is similar to the ambient light, but will instead imitate a sky and ground by passing a sky color and ground color. Let's pass a white and dark gray color for now to clearly see the differences. Let's also pass the intensity that we created before. The result will already look a lot more realistic while still very performant. The third light, directional light, will be a bit different from the previous 2. It's a light that has only one single direction, as if the source is infinitely far away. A very common use case is imitating sunlight because the sun is so far away that it seems like the sun rays are parallel. Let's implement it by adding a directional light and setting the position and intensity. And this will already work, but it's hard to see what exactly happens here, but therefore we can use different helper classes using the use helper hook formula. We need to create a reference to the directional light and pass that and the instance of the helper class to the use helper function. Once those are passed, you will get autocompletion for the other parameters that you can pass in. Those are the arguments that get passed to the directional light helper constructor. In this case, we can set the size and color of the helper. It's good to know that changing those values has no effect on the light itself, only on the helper. The directional light itself has, for example, no boundaries, which is different from what you see in the scene with our light helper. Now you might remember that we set the position at the beginning, and this was because the directional light needs to have a position and a target to determine the direction of the light. The default target is the center of the scene, but you can also move that one around. Note that you have to add the target to the scene first to let the directional light actually shine towards it. Now the following light is the point light, which simulates, for example, a light bulb where lights shine in every direction from a specific position. This light is very similar to implement as the previous light. We actually only have to rename the used helper class, the light reference itself, and the PointLight JSX element. The arguments passed into the helper stay the same, which indicate the size and the color of the PointLight helper. The fifth light is the spotlight, which simulates a real-life spotlight. It shines from a specific point in a specific direction and becomes wider as it goes. Let's remove the code from the PointLight example and implement the spotlight by removing the tweakable position, renaming the JSX element, remove the intensity, rename the reference, and by changing the useRef generic type and the helper type. The spotlight helper expects different arguments in the constructor as well, so let's change that. In this case, we only need a color. Clear the tweakable properties as well, so that we can fill it with new spotlight related properties. The distance, for example, determines how far the spotlight shines. You can also see this as the height of the pilot. By changing the height, you will see that the width of the bottom circle also changes because the light shines further and therefore wider. The intensity is similar to what we've seen before, but let's add it again anyways, so you can see more clearly that the distance also affects the intensity of the light. If you don't want the intensity to lower based on distance, you can add the decay property and set it to 0. And lastly, let's add the angle property, which indicates the angle of the spotlight. Now you can see that, as expected, any surface outside of the spotlight is not being lit. One interesting thing that you might not have expected though, is that the mesh Lambert material seems to flicker a bit. I definitely recommend you to check out my previous video about materials to figure out why this happens for the mesh Lambert material, but not for the mesh foam and mesh standard materials, for example. Now lastly, let's discuss the RectAreaLight. This one emits light uniformly across the face of a rectangular plane. It can be used to simulate, for example, a bright window. Let's remove some of the previous code and change the light and helpers to a RectAreaLight and RectAreaLight helper. Be aware that for the RectAreaLight helper, you need to import from the following path instead of the standard 3 path. Remove some tweakable properties and add new ones for the width, height, and the color of the light. I set the width and the height to 3 and the color to white. We will also need to rotate the light to make it shine at the thoraces. Pass the tweakable properties to the constructor arguments and you will see a tweakable rectangle which emits the light of the color that you gave. Be aware that the color that you gave to the light helper might not be the same as the color of the light itself. And those are all the lights currently available. Make sure you're not using too many lights in your scene, because every light that casts shadow will require an extra render. How lights are being handled exactly and how to generate good looking shadows will be handled in future videos. Please like the video if you did and subscribe for more related content. Ciao!